Hey, it's Moser with protein synthesis, mRNA, and the probably future of vaccines. So, please, if you haven't already, look at the quick little PBS video that is linked on the matrix, talking about how vaccines and your immune system work in general. Once you've viewed that, let's talk about viruses specifically. Hey, there's a generic animal cell. It could be yours or mine or an earthworm's or a ladybug's or a coyote's or a bluegill's, but it's a general animal cell, and there is a virus. Now, how do viruses infect a creature? Well, I got news for you. Viruses can't reproduce. So how do they create an infection? How do you go from one single viral particle to a raging viral infection if they can't make copies of themselves? That's ridiculous. Honestly, how do they do it? I mean, in order to create a viral infection, there have to be a whole bunch of them. So if they can't reproduce themselves, well, how does that happen? Hijacking, that's how. Viruses hijack your cell's protein synthesis machinery to make copies of themselves. And once they've completely filled up a cell in your body with copies of themselves, that cell bursts like an overfilled water balloon, spilling viruses out into all the other cells nearby. Ew. As a matter of fact, some of the symptoms of the coronavirus, such as the sore throat, come from cells in your throat tearing open as they, burst, dumping viruses into the rest of your body. Ooh, yuck. So, speaking of which, why do we call it a coronavirus anyway? Well, corona means crown. And the coronavirus is not a single virus, it's a whole giant family of viruses. There have been coronaviruses around for a long time, and many of them have been in circulation for a long time, and many of them don't make us all that sick. And that sniffle you had 5 years ago, for a few days, could have been a coronavirus. There are a number of common coronaviruses that cause mild infection. They tend to not have really interesting names. They tend to be called things like EC127-3D. They only get cool names if they make the big time, meaning make a lot of people sick. So the current coronavirus that we've all been dealing with and talking about for the last few years was a novel coronavirus that showed up in 2019. Novel meaning new to humans. Its actual official name is SARS-CoV-2-19, meaning it was the second of the SARS-type coronavirus that we saw, and it arrived or showed up or emerged in 2019. Now, with that out of the way, what about this corona? Well, this corona is actually made up of spike proteins, and that's one thing that all coronaviruses have in common. What do they use these spikes for? I'm glad you asked. These spikes function much like little keys that lock onto proteins in the cell membrane of an animal cell and open the cell up so that viruses can penetrate the cell. Now, if you remember from the PBS video on immunity and vaccines, one of the things your immune system does is create antibodies that attach to these spikes, tagging the virus particles for disposal by your immune system. The other thing that those antibodies do is they block up the keys that the virus would otherwise use to get into your cells, rendering it less able to penetrate your cells. Well, that's convenient. So you should remember from your reading that there were 4 types of traditional vaccine creations: weakened viruses, killed viruses, and what I'll call the bits and pieces approach, where we take bits of the viral protein and inject those into your cells. In each of these cases, it gives your immune system a sneak peek at a virus, in this case, in a form that isn't harmful, so that your immune system can create memory cells to respond better next time. Now, there are some limitations here. With weakened or killed viruses, you first have to grow a bunch of viral particles in a lab, and that takes time. Remember, they can't reproduce themselves. So you have to grow all these viruses and then either kill them or weaken them. With the bits and pieces, it's not much better because you still have to grow all of those viruses and then harvest the bits and pieces that you're going to use in the vaccine. The new technology that has emerged in the last about 30 years is probably the future of all vaccinations, though it's being first used on a large-scale basis with the SARS-CoV-2 vaccines. It's a virus based on mRNA. So the idea being that you introduce a piece of mRNA to your cells know what to do with mRNA. It's a recipe for a protein. You give them a piece of mRNA and they'll build that protein. Once your cell builds the protein, the immune system registers that protein as a foreign substance and reacts to it, creating that army of immune cells. And once the few proteins that your cell constructed have been neutralized, creating memory cells to respond the next time that that protein is seen. That's pretty cool. One of the things this means is that as viruses change, you can just swap out the mRNA section for the new virus, speeding up the process of vaccine creation significantly. It's as if you've got a letter in an envelope that contains instructions on this year's virus, and next year, when the virus has changed a little bit, you just swap out the letter inside the envelope. The envelope's ready to go. Now, mRNA vaccines require some special care and treatment because, let's face it, mRNA is not all that stable. There's another class of nucleic acid vaccines we should talk about, and that's vaccines based on DNA. So you know DNA, it's that other nucleic acid, the one that your body uses to maintain genetic information, and that all living things on Earth use to maintain genetic information. Well, some viruses also use DNA, and one of those is the Ebola virus. It appears periodically in West Africa. There will be a pop-up flare of Ebola, and then it'll get, the epidemic will be fought back. A DNA vaccine is available for the Ebola virus. Now, why DNA and not mRNA? Good question. Take a look at this scene from West Africa where Ebola outbreaks tend to occur. Do you notice the modern electricity and refrigeration and modern sanitary conditions? Yeah, me neither. So, Ebola tends to emerge in places where you don't have access to refrigeration, you don't have access to all those modern amenities. DNA vaccines are a lot easier to keep under those conditions for a few reasons. Your cells are used to dismantling mRNA the very second that the protein is constructed. And under the best of conditions, mRNA tends to be pretty unstable. So mRNA vaccines require heavy refrigeration, actually deep freeze technology. Deep freeze. DNA is held onto by cells for a little bit longer. And though the DNA in the Ebola vaccine is still recognized by the body as foreign material and disposed of, DNA is far more stable. Think about Cheddar Man. There was DNA that was able to be recovered from his bones after 10,000 years in a cave. No deep freeze necessary. So DNA vaccines are easier to store under conditions that don't involve big old deep freezers. That's convenient. Now, you might remember, you might not, in 2014 there was an Ebola outbreak that actually did have some spread to the U.S. A few cases popped up. All it takes is somebody getting on a plane right before they develop symptoms. At this point, we knew that there was potential to make a DNA vaccine for this disease, yet no commercial drug companies wanted to pursue it. Why not? Well, again, take a look at this environment. What did it take to get an mRNA vaccine for COVID to market? It took a whole lot of money from a whole lot of governments in the US, Canada, Europe, all over the place. And it took guarantees from those governments that once there was a product available, they would purchase doses. There was pretty much a guarantee of profit for the drug companies. Again, look at this scene from West Africa. Do you think the government in this country has got the funds to promise to purchase millions of doses? No, they don't. There was no commercial motive to develop an Ebola vaccine. The drug companies just didn't see that there was any profit possible from it. Now, the vaccine was eventually developed and is stockpiled by governments all over the world, but it was done as a non-profit venture by non-governmental organizations with government funding. Interesting. There have also been trials for mRNA vaccines prior to the COVID vaccines. There was an mRNA influenza vaccine that was clinically trialed in 2015. It was in the process of getting final approval, or it was in the process of being trialed when some other virus took our attention. There have been clinical trials for a mRNA rabies vaccine. There was no significant difference in protection, and there was a cost to develop it, so it didn't go any further. But it's been done. So influenza and rabies have in fact had clinical trials with an mRNA vaccine. This is not to say that mRNA vaccines have not been without their bumps and hiccups. We've been working on this really since the 1960s when mRNA was discovered. In the 1970s was the first time that scientists were able to get mRNA into a cell and make that cell produce a protein. Wow, it's like you handed somebody a recipe and they just kept tearing it up, and finally you handed them a recipe and they said, yeah, this looks good, I'll make this one. So there was the issue, first of all, of just getting the mRNA into the cells. Remember, you're all a bunch of fatty water bags. So fats and water don't mix well. You can't put mRNA in a water-soluble medium and expect it to get through a cell membrane, because cell membranes are made of fat. You have to put it in some sort of fatty carrier. And in fact, the mRNA in these vaccines goes in a lipid nanoparticle. It's a little tiny fatty bubble. But that little fatty bubble can go through the cell membrane. Now, there were some other issues too. Your cells, your immune system is set up to recognize foreign agents, foreign bodies, foreign material. So, introducing foreign mRNA was a problem. Well, scientists discovered a breakthrough. Just as you can read the word mouse here, and when I substitute one letter, you can still read the word mouse. It was discovered that if you substituted an alternative chemical for the uracil in the mRNA, the cell could still read it to make the protein, but the body was much slower to react to it with immune function. This modified mRNA actually forms the basis of one of the companies making the mRNA vaccine. Well, look at that. Moderna is really just a word cobbled together from modified RNA. Cool. There's some interesting evidence that immune response in cells seems to be stronger when the cells themselves make the protein versus the old weakened, killed, or bits and pieces approach, which, of course, does get an immune response. But of course, your cells would be making those proteins in the case of an actual viral invasion. So maybe the body reacts to that. In other words, the future of vaccines may well lay in mRNA. It's not a new technology, and though this is the first mRNA vaccine that has gotten final approval, it probably won't be the last. That's it.